So we have different method to calculate the error functions. So if you're looking at here, so the first one is the SSE, sum of the square estimator of error, sum square estimate of error. Okay, so easy understanding here will be y equals to mx plus c, and then this one is the estimate value, and then we want to find the difference between the real value and then the estimate value. So finally, we give a square to negate the negative and then positive signs problem. And then we sum up summation, right? We sum up all the data point one by one. And finally, we get a some amount of all the error. But honestly, this one is not really good because so somehow if you have more and more example, the sum of the square estimate of error SSE will be increase and increase. It's hard to have a very subjective comparison. So usually we will use the average, the mean, okay, mean square. That means after all the summation, we take the number of turns here. So that means we take the average. So you will not be affected number by your number of data. If more and more data come, the error is almost the same. So yeah, the error will not be highly affected by the increase of number of data. And another way will be mean square, because if you always thinking about a square here, and then it takes quite a lot of time to make a huge number. So usually we have the square root. RMSE. So yeah, try to minimize the error and make it makes sense. It will be more make sense to the humans. But if you are talking about the computation power, if you take the square root, so it takes more and more computation power. So usually we'll use the MSE or RMSE, but if you want to save the computation power, MSE is good. Or just simply use the absolute sign, ABS. So this one is good. Yeah, I will say that. So here we take one of the example to calculate the error. So we take SSE, sum of the square estimate error. Okay. So we have 1, 2, 3, 4, 4 point here. Again, we have 4 point. And then we have the estimate linear equation y equals to 1x plus 5. 1x plus 5. Okay. So you can do it by calculate the estimate value and the real value one by one. So you input the x equals to 1, 2, 2, 4, right? So here you have the 1, 2, 2, 4, and then y equals to mx plus c, right? You have the estimate value by using the linear equations, and then you also have the true value, the correct point. So the correct point is here 5, 8, 6, 13, right? So we put the correct point here, and then we use the square root, square, and then we calculate the final result here. Okay. So the final result, the sum will be 19. So this 19 will be used to evaluate the I would say that the effectiveness of these linear equations. So is the best model, or is there any better model that we can have? From here, we still want to find a better linear equation to represent all the data set. So the linear equation is related to all the data set. So yeah, it's related to the error. So suppose that y equal to 1x plus b here, we knock down the m, the slope, here to 1x. And then we want to find different combination of y-intercept. For example, y-intercept equals to 1, 2, 3, 4, 6, etc. So we want to find which one is better. So by changing the y-intercept, so the linear equation will be also changed. So we want to find the error of y-intercept 1, 2, 3, 4, 6, and then find the best model of our current data. So similar to your previous slide, we use the SSE, right? So we plot the different linear equations. And then by plotting different linear equations, for example, this one b equals to 0. So we have the different error between the different data point. So we have the different error. Suppose here b equals to 0. So we sum up all the things together, sum up all the error together is 140 something or 150, I can't remember well. It's here, the data point. Then we try another, b equals to 10. So we have the b equals to 10 here, and then the data points, we sum up all the error together, and then we have the data point here. So it should be 80 something. Yeah, 80 something right there. We can also plot different, for example, this one, b equals to 6. And then we will have different error with the data point. And again, we sum up different error together. And then we have here 20 something. So by plotting all the points, and then we can have a parabola. Parabola is here. And then this kind of parabola, this kind of curve. So we can find a minimum values. Can you see that? So we have the minimum value. And then we usually will tune the y-intercept together with slope, and then turn it into this kind of curve. And then throughout this curve, we will try to find the minimum value of the error. So here is different kinds of the b value, so we can have different kind of the slope value. Okay, so this one is y-intercept. We can have different value of the slope, and then plot the SSE, and then we can find the minimum value of the slope and then y-intercept, so that we can have the best linear equations. So yeah, because it's linear equation, so only we have two parameters. When we log the slope, then we only turn the y-intercept, right? So when we fine-tune the y-intercept, so we have the minimum error of this y-intercept. So here we can return this one value. Mathematical way presentation. So here is we have the differentiation, right? We are going to find the change of the SSE based on the change of the y-intercept, and then we want to have the differentiations, and then we want to find the local minimum. So if you have studied the differentiation before, so this one, the change of the curve can be used this kind of mathematical formula to define, and then you can find the local minimum point if this one is only a curve here and one turning point. More about mathematics, so differentiation, most likely we are going to find the tangent of the curve. So for each point, so we will have a tangent here, and then the tangent, the slope of this tangent, the straight line, the green line, will become more close to 0. Right here is the positive, and then here is the 0, and then it turns to the negative. So here we have the turning point. And then if you have studied the differentiations, so this one, the slope is can be calculated, and then the turning point can be calculated. So all the things is about mathematics. But if you haven't studied differentiation before, it's not too bad, because first, it will not be included in our final quiz. Second, you will learn in your university study again in your mathematics 1 and 2, something like that. So you still have the chance to catch up the mathematics equation, especially when you want to move into the research area. Yeah, when you are changing the y-intercept, so that means the bias, right? Y-intercept, and then this line will be moved, and then it will get close to 0. See? And then finally turns to positive again. So for to find the minimum loss, so easy to understand it, we just want to find the slope that is equal to 0 here. The tangent is equal to 0. So here is the positive, and then here is the negative, and then there is a turning point. The turning point is 0. And we want to find the turning point of the SSE, and then turning point of the SSE is the slope of the tangent that is equal to 0. Exercise, so after we have logged the slope, then this time we log the y-intercept. Okay, so we change the slope. So slope now we have the negative 1, 0, 1, 2, 3, etc. So repeat the previous step, and then try to calculate the error, and then try to calculate the best slope that we can have. Okay, so yeah, we are changing the slope here. The y-intercept, can you see that? It's still 5, 5, 5. We haven't changed the y-intercept, but somehow we change the slope. So the slope is changing from here, this point, and then to this one is anti-clockwise, right? Anti-clockwise, and then we change the slope by rotating the linear equation by rotating the line. So you can repeat and then calculate the SSE. So when you have prepared the y-intercept here, and then you also prepare the slope here, right? So somehow you can come up with a table that represents the SSE, sum of the square estimate error. So here, so you will see a relationship of B, y-intercept, and then relationship of the slope. And then, yeah, because you have the two input and one output SSE, so definitely this one is a three-dimensional graph. So this one is the slope, and then this one is the y-intercept, and then your error will be changed based on the slope, and then also based on the y-intercept. So in a better way to calculate the linear equation, so most likely we travel through this surface and then find the local minimum, find the minimum. And then the minimums will be the best linear equations of your linear regression. So that is the minimum point, and then we want to find out this minimum point by tuning the slope and also the y-intercept. And this method is called gradient descent. Okay, so we are here. We want to find the weights that can get out from the mountains, right? So how can we find the way to get out from the mountains? Definitely you will not move to the pit, right? So we will use your sense to move a little bit lower until you find a way to escape from the mountain. So that is called gradient descent. Decrease the slope, decrease the slope, and then find the local minimum by using the y equals to mx plus c, right? By tuning the slope and then the y-intercept to find the minimum error that you can find inside your model. So if you are saying you want to learn more about the procedure or the step how to do the gradient descent, so it's easy. You will just start somewhere randomly. Again, randomly, similar to the new level. All the things we start is randomly. We start somewhere randomly on the mountains, and then we find the best direction that can reduce the error a little bit, So repeat the step of the two, M and B, until the certain loop. So most likely if we are running the k-mean cluster, or if we are running the other things, we always coin the loop. So how many computation power, how many calculation you want to put it into the gradient descent to find the minimums. So suppose that the more the increased number of terms can improve the error. But somehow, if the error, the improvement of the error cannot be observed easily, we'll stop the improvement and then we'll stop the calculations, and then that is how we run the gradient descent. The gradient descent in an abstract way is just like here. You start randomly on a curve about the error of the if it's 2D, it's about the error of the slope or y-intercept. If it's 3D, then it's a surface. Okay, so by calculating the error, the square value of the error, and then you will find a small area, and with the small area, and then you can have a better and better linear equations for your regressions model. More about the gradient descent. So suppose that if your slope is positive, so somehow you move to the left to find the minimum point. If your point is, if your slope is negative, so somehow you move to the right to find the lowest point of the error, the SSE. So you want to find the optimized solutions. If your error is large, so you move faster. If your error is small, so you move smaller. Okay, so the change of the slope or change of the each step will be small. But if your error is large and then the slope is really large, right? So you move faster and then you change the point in a bigger step. So you want to find or complete the whole calculations in a more faster and faster way. So that's why we use the SSE or MSE. So it try to enlarge the effect of the error. So when we enlarge the effect of the error, so when it's not close to the optimized point, to close to the best value, the best linear equations, so the value will become bigger. But it's close to the best value, so the error will be smaller. And that is how we find the best value or best model. Okay, so that is how we move faster and then faster and then slower to the optimized point, to the best value that we can have. So when you want to visualize into a 3D way, so that is the situation. Here is the slope, and then here is the y-intercept, and here is the error. If it's a perfect surface, so they only have one minimum point, one local minimum point. And then by putting the error, so we can find out the best solutions of this surface, and then that is gradient descent. By finding the slope, the best point of the slope, and then the best point of the y-intercept, so we can have the best error, and then we can just go to the error in a really fast way. So that is one of the perfect situation that we can have. In our housing example, so this is one of the perfect, right? So we have a perfect line of slope, perfect line of y-intercepts, and then we can find the error in a really small number of terms, number of loops, so it's easy. If you want to learn more about the linear equation learning way, so here we have a machine learning graph, and then you can plot it. You can also go to the statistic kingdom. So there are lots of ready to use tools. SPSS IBM is also really good and is fantastic. So, but somehow not all of you guys have this kind of software at home, and all these kind of online tools can help you to plot the graphic and then display to your other subject or other subject lecture to show that you have a scientific way or machine learning way to get the result. So our previous example is just like here. So we are moving on a galaxy, in a galaxy on a surface, and then we have a best local solution here, right there. But again, this surface is just like our galaxy. We think that our sun is the biggest, largest object in our world, right? But honestly, it's not the situation. Maybe in our galaxy, right? So we have different object that is bigger than our sun. Okay. So they may be here, they may be there, they may be somewhere else. I don't know. If we are just using the gradient descent, so it will be easy fall into a local minimum, and then we cannot find the global minimum, the biggest solution, the best solutions, the biggest object in the galaxy, the best solutions in our linear equations. But again, so this one can be solved if you just repeat the random starting point in your galaxy. So if you repeat lots of the random starting point in your galaxy, so most likely if they can go to the same point, we think that this one is the global minimum. But you will just do it once, so that is not good, because if you just do the experiment, so somehow this one is just local, it's not the global. So we put different random starting point and then find which one, or whether we can focus or whether we can jump into a local minimum. That is one of the important methodology or important point in our linear regressions or in this kind of gradient descent problems. Then, as I have mentioned before, the y-intercept, the bias, you can edit, and then for the linear equation, usually it is not only about one or two variables. So it will be multiple regressions. So you will have the x1, x2, x3, x4, x5, etc., etc. So for example, in here you have the cells, pi cells, you have the width, you have the apparatus 1, etc., etc. So when you turn it into something like that, so it's not easy to draw or to identify the relationship between the y and then the x1, x2, x3. Usually we will plot all the things and then we'll have the 2D first, 2D graph to plot the graphics, and then we will have the 3D and etc. etc. We will have the I would say the general understanding of all the distribution first, and then we try to find out some meaningful relationship and a meaningful situation for us to do the regressions. So always, it's not always a standardized solution. So most likely it's a try and error, but we have a directions, and then we use this kind of thinking process to guide us to find the best linear equations. In your face-to-face and also the online exercise, we have designed situations, and then we will teach you how to process. It's not so big, it's only 1,300 data to process the error and then find the best solutions for the situations. The regression model, multi-regression model, so maybe it's not only a line, maybe it's a plan, okay? Maybe it's a surface, maybe it's a volume. So it really depends on your number of x1, x2, x3, number of input dimensional. So if the input of dimensional change, so somehow they will have more and more hyperplane or more and more different kind of higher dimensional polygon to separate your data. And then to find a best surface, or to find a best mathematical formulations to identify your problems. Like here, so in this situation, we have 1, 2, 3 parameter, and then this parameter try to have a three-dimensional graphic, and then we need a plan to calculate the situations. But honestly, this one, if it's a half-dimensional plan, so not only a linear equation can solve it. So mostly you need some nonlinear methods, support machines or other AI or other mathematical tools to solve this kind of problem. If you want to go into this one, or if you have interest about this part, study more about the machine learning, and then you can have it more, especially when you want to go to research. So that is the, I would say, the AI data analytics 1, 2, 3, and then that is the things that you have to encrypt before you go to the graduate school. Yeah, that is the situation, and then we use the plan to calculate error, and then we want to find what is the best model for our study. But this one, it's a PD or OT, so most likely you will not touch this kind of mathematical model. You give it to some computer science guy, or you will give it to some mathematical guys to complete this kind of study. Yeah, and then that is the case of the linear equations. And sometimes you will not only have the linear relationship, you have the non-linear, a curve relationship. And maybe the data will go like this one, okay? So you need to do some clustering before you continue to do your linear regressions. So find an equation to fit all the things. You would like to cluster the data first.